Okay, so we're in the module where we're looking at solutions to differential equations. And today we're going to do Runge-Kutta. So I'm going to do a couple derivations of this method. So here's the first derivation. Okay. Yep. So the first derivation is to find. So we want to find y equal to y of x when you know dy dx is defined by a function of x and y. All right, so we basically know that the slopes at any given time are equal to a function of f of x and y, and that function is provided. And we give you an initial condition that y of some x naught is equal to a value y naught. And our goal is to start with x naught and to find y naught. All right, so we find y of x naught, and that value we consider to be y naught. That's going to be its approximate value. Then we'll know x1, and we seek to find y of x1, and its approximate value is y1. And so we will keep doing this until we go up to some xn where we choose to stop. We will find y at xn, and its approximate value will be yn. So now, if I just look at the basics of Taylor series, I would know that y of xn plus 1 minus y of xn, well, this is simply the integral from xn to xn plus 1 of the derivative y prime at x dx. Okay, so that's what we get when we integrate. And so now we're going to get that this is simply xn plus 1 is some xn plus h. And then this is y prime at x dx. So this is now just using the fundamental theorem of calculus. All right, and that's very simple. Now we also learned Simpson's rule, okay? So with Simpson's rule, if we wanted to compute the integral from a to b of f of x dx, we took this as h over 6, and this is y prime of x plus 4 times y prime at the x in between there, hn plus h over 2, plus y prime at xn plus 1. Now here, this is a little bit different. Let me explain to you the difference. If you recall, when we first talked about the trapezoidal rule and the Simpson's rule was h over 3. And the reason why it was h over 3 is because we took an interval an, a to b, a to b, and we divided it up into n intervals. So let's say I divide it up into 4 intervals. All right, so here n is equal to 4. So when we did the trapezoidal rule, we used for trapezoidal rule, Tn, we used that H was B minus A over N. So if you use that H in the formula, then your trapezoidal rule, then in Simpson's rule, you would use the same H for N, and that would give you where you would have the H over 3. But if in Simpson's rule, which some people write this as, so this is for Simpson's rule, where H, so this is Simpson's rule, where H is actually only this size. So the H here, so the H for this would actually be this big. And that's why we get B minus A over 6, okay? We get H over 6. All righty. So when we do that, we know that this point right here is a midpoint. So that's the midpoint between xn, which I should have right here. This should be xn. That's the midpoint between xn and xn plus 1, where the midpoint is h over 2. All right. Plus the xn. Okay. So now I want to split this 4 times y prime at xn plus h over 2 into 2 times y prime xn plus h over 2 plus 2 times y prime of xn plus h over 2. So now we want to replace the right-hand side with the true values of the slopes. Okay, so the first one, which is y prime at xn, that's simply f of xn yn, and I'm going to give that a name of k1. Then the second slope, which is y prime of xn plus h over 2, that is equal to f of xn plus h over 2. And then this is yn plus, we're going to multiply it by k1 times h over 2. Okay, so that's the next approximation. We're going to call that K2. Then we're now going to do y prime of xn plus h over 2. But this time we're evaluating it at xn plus h over 2. And this one is yn plus, we've moved to a new point, h over 2, and I'm going to call that K3. And then the last one, which is y prime of xn plus h. So that is f of xn plus h times yn plus k3 h over 2. And no, that should be just be a full h. And that is k4. And then we still have what we had before. So now we get yn plus 1 is simply h over 6 times k1 plus 2k2 plus 2k3 plus k4. And this is a fourth order scheme that we use to solve dy dx is equal to f of x, y. And so that is the absolute value of y of xn minus the true value yn is something less than or equal to a constant. And then we have h to the fourth power. Okay, so this is how it works. So say we were going to compute, here's an example. So we have dy dx is equal to negative 6 xy, and y at 0 is equal to 7. So our f of xy is negative 6 xy. Okay, now we talked about using Euler, and we also talked about using improved Euler, which you will be doing in your project, and you will also be doing Runge-Kutta in your project. Okay, so the first thing you need to do is to compute K1. Oh, okay, so we know that X naught is equal to 0. And let's say we're going to go to X1 is equal to 0.2. So that means our H is 0.2, and we're trying to find Y of 0.2. So we only want to do right now one iteration, just one. Okay, now your code works rather fast, and that's really nice, so you can move forward fast with your code, but we're doing this by hand. So our first thing is K1, and K1 is f of 0, 7, which is negative 6 times 0 times 7, and that's 0. Okay, so now we need to compute K2. K2 is f of x plus our xn plus h over 2. And then we have yn, so this will be x naught. Let me do x naught plus h over 2, and y naught plus k1 times h over 2. Okay, so x naught plus h over 2 for us is simply 0. H over 2 is 0.1. So this is 0.1. So this turns out to be f of 0.1, and y naught, as we know it, is 7. And K1 was 0, so I don't have anything. So this is negative 6 times 0.1 times 7. So that's negative 4.2. Okay. K3 is f of x naught plus h over 2 again, but this is y naught plus k2 times h over 2. So now our x naught and h over 2, this part is still 0.1. So that's okay. But the y naught now is still 7 plus k2 is negative 4.2. H over 2 is times 0.1. Okay, so now we need to be able to compute. So this is 7 plus 4.2 or 0.42, and it's negative. What did I do? 7. Yes. So this becomes 6.58. All right, so this now becomes f of 0.1 times 6.58, which is negative 6 times 0.1 times, actually, this is times 6.58. So times 6 times 0.1. So that's 3 point, and it's negative 948. Okay, and our last one is K3, K4, I apologize, is equal to f of x naught plus h. So we've actually gotten to the point where we want to go. And this is y naught, and this is K3 times h. So x naught plus h, that's 0.2. And then this is y naught, which is 7, plus K3, which we've already determined to be negative 3.948, times the full h, which is 0.2. So now when I take that, multiply that by 0.2, and then I subtract that from 7, I get 6.2104. Okay, so this is now f of this time 0.2 and 6.2104. So this is negative 6 times 0.2 times 6.2104. And that is negative 7.45248. Okay, so now I know that my, excuse me. So now I know that my yn plus 1 is simply going to be yn, which was 7, plus h over 6. So that's h was 0.2 divided by 6 times, the first value was 0, plus 2 times a negative 4.2, plus 2 times a negative 3.948, plus 1 time, plus a negative 7.452. 0.45248. Why didn't it? There we go. And for some reason, I am not believing that, but let me see. What did we start off with? Y naught is equal to 7. I do not believe that answer. Under no circumstances do I believe that answer. Why are all my K's? What did I do wrong? I did something wrong. Okay, the error is 7 plus. I have 0.2. That's H times K1 plus 2K2 plus 2K3 plus K4, end of that thing, and then divide by 6. And it won't calculate it for me. So why won't it calculate it? Oh, because it doesn't have a times here. Yay. Now that's the answer. Okay. 6 point, undo that. I don't know how that moved. Okay, so that's 6 point there. So therefore, let's see what we would truly get as an answer. So now the true answer, y at 0.2 is equal to 7 times e to the negative 3 times 0.2 quantity squared. Okay, I knew right away that that original answer was wrong. So I'm going to take 7, multiply it by e to the negative 3 times 0.2. And I get, wow, that's beautiful. Okay. I get 6.20844. Okay, not a bad solution. Okay, so this is the true value. This is the approximate value. And we only did one iteration. Okay, so that's Runge-Kutta. Obviously, you do multiple iterations to get a solution. Okay, so the geometric interpretation is very similar to the geometric interpretation of the Euler's method, except that you have 4 slopes that you are averaging. Okay, so for the geometric interpretation, we are averaging 4 slopes. All right, and so therefore we end up with the same method. All right, so let's look at another derivation. This is the way we can derive some possible solutions here. I already did this one. Okay, so the first thing is, as you can see, the error goes down by h to the 4th. All right, so if I reduce my h by 2, what will my error go down by? Hello?
Hi.
Hi. If I reduce my error by 2, so I go from h to h over 2, what happens if I reduce my step size? What happens to my error? It goes down by?
Goes down by 2.
Actually, let's see. So we know that the error in Runge-Kutta, so the error goes like O to h to the 4th. So therefore, if I go from h to h over 2, my error goes from h to the 4th to h to the 4th over 16. So I reduce my error by 16. Just by reducing my step size by 2, I reduce my error by 16. Okay. All right. So let's suppose F has the general form. And actually, I want this to be capital F, not little f. So capital F is going to look like C1 times F of XY plus C2 times F of X plus alpha times H, comma, Y plus beta times H times F of XY. So we're assuming that it has that form. Okay, so we need to determine C1, C2, alpha, and beta so that the truncation error is minimized. Okay, so we're going to use the Taylor series. For a function of 2 variables. To expand that second part. So we want to expand F of X plus alpha H, Y plus beta H, F of X and Y. Okay, so now if you remember F of X plus A, Y plus B, that's just simply F of X, Y, plus the partial with respect to X times X at XY times A plus the partial of F with respect to Y at XY times B, plus we have second order partials, which are 1/2. We get F sub XX at XY times A squared, plus we get 2 times the mixed partial FXY times AB, plus we get FYY times B squared, And we can keep doing this if you guys remember Pascal's triangle. So here we're going to let A just be alpha times H, and we're going to let B simply be beta times H times F of XY. All righty. So now we're going to get F of X plus alpha H, Y plus beta H F. I hope you guys are okay with me just writing F, because that's what I'm going to do. So this is F of XY plus alpha times H times F sub X plus beta times H times F times F sub Y plus 1/2 alpha squared H squared times F sub XX plus 2 times alpha beta. I'm going to have H squared, and I'm going to have F times F sub XY, plus I'm going to have beta squared, H squared, F squared times F sub YY. All right, plus something that is order H cubed. Okay, so this now becomes equal to F plus, I can factor out the H and get alpha F sub X plus beta times F sub Y. And then I can factor out the H squared, and I can get alpha squared over 2 times F sub XX plus 2 alpha beta times F sub XY plus beta squared over, get rid of the 2, I apologize, no 2. Plus beta squared over 2 times F squared times F sub YY. Okay. So now F, my original F back here was C1 times F plus C2 times this thing. So this is C1 times F plus C2 times this whole thing, this whole thing, F plus H alpha F sub X plus beta F sub Y plus H up, that's the end of that part. Plus H squared times alpha squared over 2 F sub XX plus alpha beta F of XY plus beta squared over 2 F squared F sub YY. So all of that's multiplied by C2. That's a small bracket with a bigger bracket. Plus O of H cubed. All right, so the truncation error That we're going to call Tn of y bar. Okay. So now we get Tn of y bar minus, it's equal to y bar of xn plus 1, that's the true value, minus y bar of xn minus h times f of xn y bar n. Okay. Now y bar of xn plus 1 is equal to y bar of xn plus y bar prime of xn times h plus y bar double prime of xn times h squared over 2 plus y bar triple prime of xn times h cubed, I don't want that, oh yeah, times h cubed over 6 plus something of order of h to the 4th. So now I get T n of y bar is equal to y bar of xn plus 1 minus y bar of xn minus h times f of xn y bar of xn, y bar n. So now I can plug in what I have for y bar of xn, and I end up with y bar prime of xn times h plus y bar double prime of xn times h squared over 2 plus y bar triple prime of xn times h cubed over 6 minus h times f of xn y bar n plus O of h squared, h to the 4th, I apologize. Okay, now let's plug everything in. This is going to give me f, little f times h, plus f sub x plus f sub y times f times h squared over 2 plus, this is long, f sub xx plus 2 f sub xy times f plus fyy times f squared plus f sub xy plus fy squared f times h cubed over 6. Okay. Minus still h times, this is long, guys, C1f plus C2F plus C2 times H times alpha Fx plus beta F times Fy plus C2 times the next term, which is H squared times alpha squared over 2 Fxx plus alpha beta F times F sub xy plus beta squared over 2 times F squared times F sub yy plus O of H to the fourth. Okay. So now we get Tn of y bar equals H times F minus C1F minus C2F. All right. Plus H squared times 1/2 F sub x plus 1/2 F sub y times F minus C2 alpha F sub x minus C2 beta F times F sub y. That's the H squared term. The H cubed term is 1/6 F sub xx plus 1/3 F times F sub xy plus 1/6 F squared times F sub yy plus 1/6 F sub xy plus 1/6 F times Fy squared minus 1/2 C2 alpha squared F sub xx minus C2 alpha beta F sub xy minus 1/2 C2 beta squared F squared times F sub yy plus O of H to the fourth. Okay, so let's get rid of the first piece, the order H piece, and so that gives us 1 minus C1 minus C2 is equal to 0. So that kills off the order H squared, order H. Then I have 1/2 minus C2 alpha, that is multiplied by F sub x, plus 1/2 minus C2 beta times F sub y, and that is equal to 0. All right, so 3 equations, 4 unknowns with that's an undetermined system. So we have 3 equations. I think 4 unknowns. So this is an underdetermined system. Okay, so we have C1 plus C2 is equal to 1. We have C2 times alpha has to equal a half. And we have C2 times beta has to equal a half. And we still need yet something else. So we have C1 is 1 minus C2. And then alpha equals beta. And that is a half C2. So therefore, if we do that, our Tn of y bar will be order h cubed. So we need to choose C2 to minimize the O of h squared error. All right, higher order formulas can be created and analyzed in a similar manner. But the algebra is very complicated. Okay. So you can do that. You can assume, whoa. Assume that F is equal to the sum J equal 1 to some M of weights Cj times Vj. So the VJs are the VJs are the I don't know why I can't get the word out of my mouth. The slopes, couldn't say it. So V1 is equal to F of XY. V2 turns out to be F of X plus alpha H Y plus beta that's ugly beta. Plus beta 2,1 H F at XY. And you can keep doing this until you get to VJ is equal to F of X plus alpha H Y plus the H times the sum I equal 1 to J minus 1 of beta JI. times VI. J equals 2 all the way up to M. So Runge-Kutta is just a fourth order scheme. You can do this and you can make it have as many values that you need. So here CJ, alpha and beta JI are chosen to make the leading terms in the truncation error equal to 0. Okay. Now there is a connection between the number of evaluations M and the function of the function and the maximum possible order that can be attained. For the truncation error. Okay. So actually, if you look at this, this is a nice chart. So the number of function evaluations and the maximum order method. So if you have one evaluation like Euler, okay, it's at most order H. Remember, we had modified Euler, had 2 evaluations, it's at most order H squared. We didn't talk about a 3 evaluation method, but it's at most H cubed. Runge-Kutta is a 4 evaluation method, and as we saw, it was order H to the 4th. If you have 5 evaluations, it can still only be no more than H to the 4th. If you have 6 evaluations, it could be no more than H to the 5th. 7 evaluations is a 6, and 8 evaluations is 6. Okay, so that's the best you can do that they've been able to prove in creating these methods, okay? So we've already done that. All right, so let's look at our algorithm for our method. Okay, so I'm going to do the method. So here's the actual fourth order method. Oh, good, we'll have time to get through all of it. So we did derivation. Okay, so derivation 1, I'm going to make this 1, and then derivation 2, I'm going to make this 2, and then 3 is going to be our, it looks awfully big. Did I mess with the size? I don't know. Let's see. There we go. Okay, so the fourth order Runge-Kutta method. All right. So a lot of times we use V just because of the way it was derived is equal to yn plus h over 6. Actually, this is really no different than how I wrote it before. Did I write the whole method out? Yep, I did. Here it is. Okay, so let me write it just because I wrote it in the middle of stuff and I haven't just clearly given it to you. Okay. K1 plus 2K2 plus 2K3 plus 2K4. Oh, nope, there's no 2 on that. There's just a K4. Okay, and so K1 is f of xn, yn. K2 is f of xn plus h over 2, yn plus k1, 1/2 h, well, h over 2 k1. H over 2 times k1. And then k3 is f of xn plus h over 2, yn plus h over 2 k2. And then k4 is f of xn plus h, yn plus h, k3. All righty, so here's the algorithm. I want to do so much, but there's so much we still have to do, and we are in the second, we have 1 month, right? So maybe 8 lectures. Not even that, because we lose 1 for Thanksgiving. So I'm looking at maybe 7 lectures. And we haven't even touched matrices. And that's a bear. Okay, so here's the algorithm. All right, so you're given y prime is equal to f of t and y, a less than or equal to t less than or equal to b. Okay, so y at alpha, y at a is alpha. All right, and so now you need to input. So here's your input. Your endpoints A and B. and an integer n. It's how many iterations you're going to do, and your initial condition. You need to know alpha. All right, so then you will compute H is equal to B minus A over N. Okay, you will let T start off as alpha and Y. I'm sorry, T starts off at A and Y starts off at alpha. And go ahead and print those. Okay. And then I, for I equal 1 to N, compute K1. And that's just the function eval of T and Y. Okay, so you've defined the function in your code. So your code knows how to evaluate this function very quickly. You define K2 is going to be F of T plus H over 2, and then you're going to use Y plus H over 2 times K1, and then K3 is going to be F of T plus H over 2, Y plus H over 2, K2, and then K4 is going to be F of T plus H, Y plus H, K3, and then you'll get Y is equal to Y plus H over 6, and then you'll have K1 plus 2K2 plus 2K3 plus K4, and upgrade your T to be A plus I times H. And then you can print out your T and your Y. And then that's the end of your loop. Okay, you just go back. All right, so that is that. All right, so the nice thing about it is your step size can be larger. So with Runge-Kutta, you can increase your step size since your error goes like order of H to the 4th. So now if you run your code and you run the same H with Runge-Kutta as you do with Euler's and improved Euler, you will see that your solution to the Runge-Kutta will be significantly better because you're running it with the same H, but your error is much smaller. Okay, so there's also Runge-Kutta-Fehlberg. Trying to see, do I have time to even go through Runge-Kutta-Fehlberg? Oh, I know what I want to talk about, systems. Okay. All right, so let's talk about systems. Now, if we have time, we'll go back to Runge-Kutta-Fehlberg. All right, we'll see. Okay, so here's a system. So y prime is equal to f of t, y, and u prime is equal to f of t, y, and u. Okay, so you are given that y of a is equal to alpha 1 and u of a is equal to alpha 2. All right, so we want to solve this. So this could be an example. Y prime can equal t, the sine of I'll make it even easier. U plus t, and then z prime. I'll make this u minus t and make this t minus u. T minus y, t plus u. I don't know how I went to z, guys. I don't know how I went to z. Okay, so now again, I have to give you something like y of a is equal to alpha 1 and y of b, a is equal to alpha 2. And so now we can solve the system, but we have to evaluate everything at the same time. Okay, so we do it at the same. Yes.
Is it y of a for the second line?
Did I do what?
The second line, is it y of a?
This is supposed to be a u, but I don't know why I keep writing a z.
Okay. Okay.
I don't know why I keep writing z. I'm not sure. That's crazy. Okay, so again, let's go back to what we have for our Runge cutter with our algorithm. So with our algorithm, we're going to need the same stuff, okay? So we're going to need this, but I'm going to modify it. We have 3 minutes. Okay, so we need input A and B. Now we need 2 initial conditions, alpha 1 and alpha 2. Okay. We also are going to set y equal to alpha 1 and beta u equal to alpha 2. All right. So now we're going to do, we can print T, U, T, Y, and U. Okay. So now we need to have a slope for each one. Okay, now you can call it however you want. I would call it something like KY1 or YK1. So I would have YK1 would be F of T, Y, and U. And then I would have UK1. Did I call it? Please tell me I called it G. Oh, Lord. It can't be F. This has to be G. Okay. All right, so we're not going to be able to finish. This would be G of T, Y, and U. And we will finish this on Monday. And we'll see where we go from there. I have to look at the syllabus and see what all we have to do.